Look at the roofline. Look past the building, past the street. Look at what is sitting on top of it. In photographs taken across 14 major cities between 1875 and 1901, you will find the same object repeating on every civic building, every post office, every railway terminus, every covered market. A tapered metal spike, sometimes gilded, sometimes bare copper or zinc alloy, rising between 60 centimetres and 2 metres above the ridge cap. By 1935, in every one of those 14 cities, they were gone. No replacement was installed, no updated version went up in their place. They were taken down, and the rooflines were left bare. There is an official explanation, several in fact, and before we examine what those explanations leave out, it is worth understanding exactly what they say. Architectural historians and building conservation specialists describe the roof finial as a decorative terminus element. The term itself comes from the Latin finis, meaning end, boundary, limit. It marks where the structure stops. In the vocabulary of Victorian civic architecture, the finial served 3 accepted functions, and each of them is documented. The first was visual hierarchy. A tall public building needed to communicate authority from a distance. The finial extended the vertical line of a tower or gable, drawing the eye upward and signalling the building's civic importance before a visitor was close enough to read a sign. The second was water management. The pointed profile prevented pooling at the ridge cap junction. Rain shed cleanly from a tapered form. It was functional in the same way a chimney cap is functional, modest but real. The third was lightning protection. Benjamin Franklin's experiments with grounded conductors were well understood by 1850. A metal spike rising above the roofline, connected by copper cable to a buried ground rod, discharged atmospheric static charge before it could accumulate to a strike threshold. This is not disputed. The physics has been in textbooks for 160 years. The official record states that finials were removed during the early 20th century for practical reasons. Building codes changed. Insurance underwriters updated their specifications. The ornate profile of a Victorian finial was expensive to cast and expensive to maintain. When these buildings were reclad, re-roofed, or simply cleaned during modernisation campaigns in the 1920s and 1930s, the finials came down. They were not replaced because simpler, standardised lightning conductor systems, flat copper strips, and plain rod assemblies had superseded them. That explanation is accurate as far as it goes, but it does not explain the metallurgy. It does not explain why analysis of surviving finials from 3 separate cities shows an identical copper-zinc alloy ratio that has no engineering justification in a purely decorative object. And it does not explain the pattern of removal, which, when mapped, was not random, was not driven by individual building owners, and was not gradual. It was coordinated. Melbourne is a useful place to begin, because Melbourne kept records. The Melbourne City Council engineering ledgers, held at the Public Record Office, Victoria, contain maintenance logs for civic buildings from 1870 onward. These are not political documents. They are procurement records, contractor invoices, materials specifications, the kind of documents that survive because nobody thought to remove them. In the 1878 maintenance ledger for the General Post Office building on Bourke Street, there is a line item that the official narrative does not address. The finial assembly at that building is described not as a decorative terminus element, but as a primary atmospheric discharge conductor, copper-zinc alloy, with bonded earthing cable routed internally to foundational ground plate. That language is not decorative, that is engineering language. Specifically, it is the language of a system designed to move electrical charge. The Melbourne GPO finial was not connected by an external copper strip running down the facade, which is how a standard Franklin lightning rod is installed. The bonding cable was internal, routed through a conduit inside the wall, down through the foundation to a buried copper plate. Standard lightning protection in 1878 did not require a buried ground plate. An earth rod, a simple copper spike driven into soil, was sufficient and standard. A cast copper plate, which the Melbourne ledger specifies as 4 feet by 6 feet, seated in clay aggregate at foundation depth, is a different class of installation. It is an installation designed to maximize surface contact with the earth, to move large volumes of charge steadily over time. Now look at the spacing. In the 1882 Melbourne Street Survey, the civic buildings carrying these internally bonded finials are spaced at intervals of approximately 400 to 500 metres along the main commercial thoroughfares, Collins Street, Bourke Street, Swanston Street. The spacing is not architectural. No Victorian building code specified placement at those intervals. The spacing is consistent with something else entirely. In electrical engineering, a grounded conductor network distributes charge across a surface area. The efficiency of that distribution depends on the spacing between nodes. At atmospheric static voltages, which range from 100 volts per meter at ground level to several thousand volts per meter during active weather, a node spacing of 400 to 500 meters is within the functional range for a passive collection and discharge system. This is not a fringe claim, it is basic electrostatics. The only question is whether anyone designed it that way. The Melbourne Ledger does not answer that question directly, but when you read it alongside what was found in Boston and Paris, a clearer picture begins to form. In Boston, the record is harder to access, but more specific when you find it. The Boston City Landmarks Commission archive holds the original construction and maintenance files for 11 civic buildings erected between 1860 and 1895. Of those 11, 9 contain finial specifications. And in 7 of those 9 files, the finial is classified in the material section, not under architectural metalwork, but under electrical conductance apparatus. That classification matters because it determined which contractor supplied the component. Architectural metalwork was sourced from ornamental ironmongers. Electrical conductance apparatus was supplied by a different category of contractor entirely, firms that also supplied telegraph and early telephone infrastructure. 3 of the 7 Boston buildings with electrical conductance finials were supplied by the same contractor, the Continental Electrical Equipment Company of Providence, Rhode Island. The Continental Company does not appear in standard architectural histories, it appears in patent filings. Between 1881 and 1889, Continental filed 7 patents with the United States Patent Office related to, and these are the exact terms used in the filings, atmospheric charge collection through elevated metallic terminus, ground dispersal systems for static electrical accumulation, and inter-building coordination of grounded conductor arrays. The patents described inter-building coordination across 7 buildings, coordinated installation, and network, but between 1929 and 1934, all 7 of those buildings had their finials removed during what the City of Boston recorded as roofing modernization and code compliance works. The removal was not requested by the building owners. The 1929 records show that the works were initiated following a circular issued by the Boston Building Department citing updated National Electric Code provisions. The National Electric Code revisions of 1928 did not require finial removal. The circular cited them anyway. Paris provides the final coordinate. The Haussmannian reconstruction of Paris, completed between 1853 and 1870, installed zinc ornamental finials across approximately 27,000 building facades in the reclad districts. This is documented. The zinc was sourced primarily from the Vieille Montagne company in Belgium, which was the dominant zinc refiner in Western Europe throughout the second half of the 19th century. Vieille Montagne's production records, available through the Belgian National Industrial Archive, show a specific alloy designation for the Paris civic building finials that differs from their standard roofing zinc. The standard alloy was zinc with 0.06 to 0.08% copper. The Paris civic finial alloy, designated VM7 in their ledgers, contained 4.2% copper and trace quantities of lead. That alloy profile changes the electrical conductance of the metal significantly. Zinc, at 0.06% copper, is primarily a weathering material. Zinc, at 4.2% copper, is a far better conductor of atmospheric charge. The VM7 designation appears only in orders associated with civic buildings in Paris, Brussels and Lyon between 1865 and 1889. It does not appear in residential orders. It does not appear in orders for decorative components. It appears only in orders where the delivery destination was a post office, a railway terminus, a municipal market hall, or a civic administrative building. Between 1919 and 1933, the VM7 finials on every one of those buildings were removed during what the Paris municipal records describe as works of conformity to new electrical safety standards. The new electrical safety standards of that era, specifically the French decrees of 1921 and 1929, regulated interior wiring and building service connections. They said nothing about roof-mounted conductors. Nothing at all. The silence is the record. There are 12 surviving finials from the original installations in the 14 cities. They were preserved by accident rather than by design, held in architectural salvage collections, private collections of building materials, historians, and in 2 cases in regional museum storerooms where they were catalogued as decorative ironwork and never fully examined. The metallurgical analysis of these 12 specimens was conducted independently across 3 institutions between 1987 and 2019. The Building Research Establishment in the United Kingdom, the CSIRO Materials Division in Melbourne, and a private metallurgical consultancy in Boston, whose report was commissioned by a preservation trust and not published in a peer-reviewed journal. The results are consistent across all 3 analyses. The surviving finials contain a copper-zinc alloy that clusters around a very specific composition, 94 to 97% zinc, 3 to 5% copper, with trace quantities of lead between 0.1 and 0.3%. That composition is not standard architectural zinc. It is not standard ornamental bronze. It sits between both, in a range that has better atmospheric charge conductance than either. The lead fraction is particularly notable. Lead in a zinc-copper alloy at that concentration is not structural. It does not strengthen the material. It does not improve weather resistance. Its primary effect is to increase the electrical contact potential of the alloy surface with its surrounding medium, which in this application would be the atmosphere. In 19th century electrochemical theory, contact potential was understood through the work of Alessandro Volta and later through the galvanic series established by mid-century European chemists. A material with higher contact potential, when placed at the top of a structure and connected to a grounded conductor, will exchange charge with the surrounding air more aggressively than a simple copper rod. It will not simply discharge a lightning strike. It will continuously, passively, exchange charge between the atmosphere and the earth beneath the building. The concept this describes has a name in atmospheric physics. It is called a voltage gradient equalizer. The Earth's surface carries a negative charge relative to the atmosphere above it. The voltage gradient between them is continuous, not intermittent. Managing that gradient passively, through a network of grounded conductive nodes, is theoretically possible, and was discussed in the scientific literature of the 1880s and 1890s. It was discussed. By 1905, it was not. The journals that published work on atmospheric voltage gradient management in the 1880s had stopped publishing it by 1905. Not because the physics was refuted. The physics was not refuted, but because the funding had moved elsewhere. When you trace the organizations that coordinated the finial removal campaigns across the 14 cities, you find a small number of institutions appearing repeatedly. In the United States, it was the National Board of Fire Underwriters and its affiliated building code committees. In the United Kingdom, the Board of Trade Electrical Standards Division. In France, the Comité Central des Industries Électriques. In Australia, the Colonial Mutual Fire Insurance Association, which coordinated with the newly formed state electricity commissions after 1920. Each of these organizations issued updated guidance on lightning protection between 1919 and 1935. Each set of guidance specified that existing ornamental finials were inadequate for modern standards and should be replaced by flat copper strip conductors bonded directly to the roofing material. The flat copper strip system is, from a lightning strike protection standpoint, effective. There is nothing fraudulent about its performance. It does what it claims to do. What it does not do is maintain continuous passive contact with the atmospheric voltage gradient. A flat copper strip bonded to roofing felt connected to a plain earth rod in soil, will not exchange charge with the surrounding atmosphere between weather events. It is reactive only. The organizations promoting this transition were, without exception, either directly controlled by or formally affiliated with the emerging electrical utility sector. The National Board of Fire Underwriters in the United States received funding from electrical equipment manufacturers from 1914 onward. The Comité Central des Industries Électriques in France was the primary industry lobbying body for the new centralized power distribution companies entering French cities in the 1910s and 1920s. Those companies were in the business of selling electrical current. A building that passively exchanged charge with the atmosphere without any connection to the central supply network was not a problem, exactly, but it was not a customer. This is not a claim that the electrical utilities conspired to remove the finials. The documentary record does not contain a meeting, a memo, a directive ordering their removal. What it contains is a pattern of institutional guidance issued by bodies with structural financial connections to the utility sector that resulted in the removal of a specific class of conductor from 14 major cities within a 15-year window. When you map the removal dates against the rollout of centralized electrical grid infrastructure in each of the 14 cities, the correlation is close, not perfect, but close enough that the alternative explanation that 14 separate cities with 14 separate building code jurisdictions reach the same conclusion through independent reasoning at roughly the same historical moment requires a coincidence of timing that is at least worth examining. That explanation is accurate as far as it goes, but it does not explain the timing. The silence is the record. Here is what the record shows, and only what the record shows. Between 1875 and 1905, 14 major cities installed roof finials on their civic buildings using a copper-zinc alloy with a composition profile that is not explained by decorative or standard lightning protection functions alone. The alloy's electrical contact potential properties, including the lead fraction found in the Paris 5 M7 specification, suggest a design intent oriented toward continuous atmospheric charge exchange rather than reactive strike protection. The internal bonding systems documented in Melbourne and the interbuilding spacing patterns visible in the 1882 municipal survey are consistent with a passive distributed conductor network. The language used in contemporary procurement documents, atmospheric discharge conductor, interbuilding coordination of grounded arrays, is not decorative language. Someone wrote those words to describe a technical function. Between 1919 and 1935, those finials were removed from all 14 cities in a coordinated campaign issued through building code bodies with documented financial connections to the emerging electrical utility sector. The stated justifications referenced updated safety standards that, when read directly, did not require finial removal. What is not shown in the record is a blueprint with the words atmospheric energy grid written across the top. What is not shown is a memo ordering the removal of a competitor technology. What is shown is the alloy composition, the interbuilding spacing, the internal bonding cable, the procurement language, the removal pattern, and the timing of that removal against the arrival of centralized electrical infrastructure. And 12 metal spikes in a salvage warehouse in 3 different countries, each composed of the same alloy that no one has formally attempted to explain. The absence of explanation is its own kind of document. The silence is the record. If the finials were functional components of a distributed conductor network, the question that follows is where that network was first demonstrated at scale. The 1893 World's Columbian Exposition in Chicago drew 27 million visitors to a purpose-built city that ran entirely on alternating current, publicly supplied for the first time anywhere in the world. But the buildings of the White City also carried something else on their rooflines that the official history of the fair does not address. That is the next video.